So this afternoon, our speaker is Dr. Jennifer Wiseman. It's a privilege to welcome Jennifer again to the Faraday, no stranger to us. Jennifer is a senior astrophysicist at the NASA Goddard Space Flight Center, USA, where she previously headed the laboratory for exoplanets and stellar astrophysics. She studied star-forming regions of the galaxy using radio, optical, and infrared techniques. Her bachelor's degree in physics was from MIT and her PhD in astronomy from Harvard. She has the rare fortune of having a periodic comet that she discovered and named after her, Comet 114P/Wiseman Skiff. She's also director of the American Association for the Advancement of Sciences program Dialogue on Science, Ethics and Religion, abbreviated to DOSA. It's a privilege to welcome Jennifer to speak to us this afternoon, and she's going to talk on galaxies, stars, planets and life, investigating a fruitful universe. Will you join me in welcoming Jennifer Wiseman?
Thank you. It is my pleasure to be here. I've been at several Faraday Institute seminars and summer courses and all kinds of things over the last couple of decades, actually, from time to time, and I really appreciate what the Faraday Institute does. Maybe I should start out by wondering, positing the question, if humanity can send people to the moon, why can't we get the sound to work on PowerPoint? But we'll leave that question for you to contemplate. So we will carry on without some of the sound that I wanted to show you today. I would like to take you today on just a little overview tour of what we as astronomers are learning about the universe through our new and improved telescopes and technology. And it truly is fantastic, and I think the more we learn about the universe, the more it fertilizes deeper questions of who we are as human beings, of human existence, and is there purpose, and is there significance, these kinds of philosophical questions. So we'll see if we can get to some of that as well in this presentation. But first I want to give you the chance to simply reflect on the beauty of the universe. So I just want you to have a sense of beauty. It's ironic that in modern civilization today, many people live in urban areas where the lights have basically drowned out the night sky. The light pollution, as we call it, has made it almost impossible for most people to have the experience that most of the ancients had by just walking outside and looking up and kind of being awe-inspired by what they saw. And yet, the irony here is that our telescopes are so much better now than ever before that with telescopes we're able to access images and sights of the universe that no one in humankind has ever had the chance to see before. So there's kind of an interesting duplicity going on. And we are seeing beautiful things. This is an example of a newly formed cluster of star. You can still see a star. You can still see the gas around the region out of which those stars have coalesced. That's my own research area, is the formation of stars and how stars form in interstellar clouds. It's an ongoing process, and it creates not only very interesting things to study physically, but it also creates great beauty as well. Well, how are we making these advances? Well, astronomers have a diverse toolbox now. So we have many different types of contraptions and instruments that we use. Here's an example, just a little montage of a few examples. We have telescopes on the ground, usually put on tops of mountains or out in deserts where it's dry and far away from lights and interference. We try to get telescopes as high as possible because in many cases clouds and even water vapor in a clear sky can inhibit our observations. And so mountaintops are favorite places for telescopes, and if you want to get really extreme, you can put them in space. So this is an example of a space telescope. This is the Hubble Space Telescope orbiting planet Earth below that you see there. It's only a few hundred miles above the surface of the Earth, so it's not very far away from planet Earth cosmically speaking, but it is above the atmosphere, and that's the whole point. So there are now quite a few telescopes in space sending back images and information using different wavelengths of light, and they have transformed our understanding of the universe. Other kinds of telescopes receive radiation that our eyes are just not familiar with. So here's an array of radio telescopes in South America. It's receiving wavelengths of light in the millimeter and submillimeter wavelength bands. This is called the Atacama Large Millimeter Array, and it is able to see through some of these dense clouds of gas and dust with great detail and helping us to understand what goes on that would normally be hidden from our eyes and from optical telescopes. There's also a whole array of different kinds of instruments within these telescopes. Instruments like different kinds of cameras, different kinds of spectrographs that take the light and spread it out into its constituent colors. So you can actually see what kinds of elements and molecules are emitting light in these different stars and nebulae that we study. And even detect their motions, things like that, their temperatures. We can do better physical analyses because of the instruments in these telescopes that are getting better and better. This telescope is about the size of a bus, a city bus, orbiting the planet, but it's been operating for 27 years. The Hubble telescope just had its 27th birthday. So many astronomers are celebrating because the telescope still works really well. And the reason this particular telescope is working so well is because astronauts have returned to it repeatedly over time to improve it. So here's the return flight on the space shuttle from the last crew of astronauts that went up to the Hubble Space Telescope and refurbished it a few years ago, put in new science instruments, refreshed things like batteries, and so the telescope is in a very good condition right now, even though it's 27 years old. So here's our happy astronauts from 2009 when they did this mission, and all the astronomers in the world are still smiling. Okay, so. It was quite an intricate operation when they, every time they've serviced it, but this is from the one in 2009 because they have to leave the pressurized compartment of the space shuttle in pressurized spacesuits and go out to the telescope that's been kind of brought into the cargo bay of the space shuttle by a robotic arm, and then they can open certain doors in the side of the telescope bus to either bring out old instruments and put in new ones, or else get in there. The hard thing is to tinker with instruments that are still there that you want to repair, and they did some of those very intricate operations as well. One of the astronauts on this trip is actually an astronomer. His name is John Grunsfeld, and he decided that this being about the 400th anniversary, more or less, of Galileo's first imaging of Jupiter and other things in the solar system, that he would take up a replica of Galileo's telescope with him on this trip. So he did indeed, and he looked out through the windows of the space shuttle using this replica of Galileo's telescope, and he said he was amazed at Galileo's accomplishments because he said the telescope really wasn't very good. Okay, yes. We're kind of spoiled now. So because we have such excellent telescopes, we can get fabulous images like this and see things in different color ranges that we might not have been able to see before, and differentiate star from star in crowded regions. That's what high angular resolution can do for you, especially if you're up above the turbulence of the atmosphere. So here's the core of a very dense cluster of stars, a globular cluster. If we were to look at this cluster from the ground, most telescopes would just kind of blend the light together. You would see kind of a smudge of light in the sky. But with a space telescope getting above the turbulence of the Earth's atmosphere, you can really get very sharp images, and in this case you can differentiate star from star, even in a very crowded cluster. If our sun, which is just a normal star, were in this cluster, it would be like one of these smaller whitish, greenish objects scattered throughout. But you can see from this image that stars are not all the same, right? You can just tell visually that they are different colors, there are when I give public talks, I often ask people to yell out which colors they see, and people will tell me they see whites and greens, and of course blue and red, and some of the more what we call smart Alecs in the U.S. Kids will say, purple and pink and things like that. And I don't see that, but anyway, we can tell that stars are not all the same, and in fact, some of them are brighter than others. Now, in astronomy, you never know whether a bright thing looks brighter because it's just closer, or whether it is intrinsically brighter. In this case, since all these stars are within the same cluster, they are more or less the same distance from us, and so the brighter stars truly are intrinsically brighter. So we know stars differ from star, and astronomers can take this image and then tease out the different stellar populations within this cluster, learning something about their ages and the history of the formation of this entire cluster billions of years ago. But it's also helpful to see things in context. So space telescopes, in particular the Hubble telescope, sees wonderful detail in a small field of view. But if you want to see the context of what you're studying, it's helpful to see a bigger field of view. So this is an image taken from a telescope on the ground that has a wider field of view. It's looking toward the center of our galaxy. So there's a lot of stars, there's a lot of dust and gas down toward the center of our own Milky Way galaxy. Some of these bright stars, it turns out they aren't actually stars, they're whole clusters. So we're going to go from this image and then zoom in and transition to the Hubble image of that cluster I just showed you. So I'm going to see if I can get this to do what it's supposed to do here. All right, so here we are, this Centaurus constellation. We're zooming in, and what looked like a star now turns out to be a whole globular cluster of stars. And as we transition now to the detail of the Hubble Space Telescope image, you can see the context of the previous image that I showed you. So now's the time to go ooh and ah. Okay, right. All right. So there's beauty and true wonders out there that we can see that we would not have been able to see without telescopes. So that's quite profound. The universe is, in fact, beautiful. It's also active, which I will get to in a moment. So here's another wider field image taken from a telescope on the ground. Surely some of you know what this region of the sky is. Anybody brave enough to say? All right, so this is Orion. I've been told that even here in Cambridge, occasionally you can see the night sky. Isn't that true? But if you can get to a dark place, Orion is very profound in the sky. This particular telescope from the ground emphasizes red colors a little bit, so you can actually see that there's some differences here in these very familiar star patterns in their colors. When I was growing up out in a rural area in the central part of the U.S., the state of Arkansas, I grew up on a farm. And so my family and I would go for evening walks every night, and the sky would be brilliant, and you could see many stars. And I remember seeing this constellation in the wintertime, and to me this looked like a kite. So there's the kite face and the kite tail. But anyway, it's others in ancient civilizations past saw this Orion more as a hunter or a warrior with a belt and a sword. And this is an old aging star called Betelgeuse up here, and a very hot star Rigel down here. But when you look at this star right here, and in fact many of these around here, just closely, even with a telescope in your backyard, you can tell that they're kind of fuzzy, they're nebulous. Astronomers kind of call anything that's fuzzy a nebula. And so when you actually look more closely at some of these nebulous regions, you find out that there's a lot more going on. So we're going to take a closer view of this reddish nebulous region right there and look at it with the Hubble Space Telescope view, which cannot see this big field of view, but does see much more detail right there in that colored region. And when you do that, you see this, okay? So this is the Orion Nebula. It's a very colorful array of gas if you look closely, you can see some very bright stars buried inside the gas. These are massive stars, bigger than our sun. And at least one of them is massive enough that it emits very powerful light, photons of light that can actually ionize the gas all around it out of which it formed. That means separating the electrons from the nuclei of these atoms. And when the atoms recombine, they emit this colorful light that we can see. So astronomers look at this and they say, not only, wow, this is beautiful, but they say, wow, a nebula, this actually tells us that star formation in this region is active and recent. Because eventually the light and the winds from these stars will blow away all this leftover gas, and all you have left is stars. And in fact, you see a lot of these nebulous regions. Many of them have these pillar-like structures. The pillars are carved out when stars form. The big massive stars form the quickest, and then their winds and radiation will go back into the surrounding gas and blow it away. But the denser knots of gas will hang on the longest, and there's shadows behind them. So in a region like this, maybe off to the right would be some very massive stars that have formed quickly, and the winds and radiation coming through would carve out these pillar-like structures. And eventually, even this remaining gas will be blown away. But in the meantime, in these denser structures, that's where we would expect subsequent star formation to continue. The lower mass stars take longer to form, but they're most likely to form in these denser regions. So we're quite interested in these types of regions as we study continuing star formation. Here's another one of these interesting column-like structures, although this is a view in infrared light. And it's a familiar view of the sky. Many of you may be familiar already with the Horsehead Nebula. This, in infrared, shows you a little bit more the ethereal, dusty emission around it, which I find quite beautiful. Although to me, this looks more like a dragon than a horse. The Bubble Nebula, I send this to people on their birthdays as nature's birthday balloon, but it's basically the expulsion from an older star showing up here as it expands outward. Quite beautiful. And then entire galaxies have beauty. So this is a galaxy here is a collection of hundreds of billions of stars and all the gas between those stars. So many stars that the light, especially in the core, just blends together, so you can't see individual stars, but you can see the beauty of a galaxy and the spiral arms that often form over time due to the forces going on in these rotating collections of gas and dust. If you look closely, you can even see background galaxies here, which are quite spectacular. So this beautiful universe is also very active. That's something that astronomers have learned over the last century. We can start with our own solar system. We have nice views of planets in our own solar system in great detail. This is Jupiter, of course, and you can see its bands of atmospheric activity. We've been looking at Jupiter time and time again with telescopes like the Hubble telescope over the last few decades to really see the evolution of the weather patterns on Jupiter. And then this region up here is what the view looks like in ultraviolet light. And it happens that Jupiter has aurorae, or auroras as we say, just like planet Earth, except very powerful. Jupiter has a really strong magnetic field. So you can watch these auroras dance around on the poles of Jupiter in ultraviolet light, which is very powerful light, and then compare it with the distribution of light that we see in regular visible light. We have a probe called Juno that has just recently arrived at Jupiter, measuring things like its gravitational field, its magnetic fields, things like that. And so we can sample with something very close to Jupiter the magnetic field processes going on and correlate it with our views from a distance of these auroras that are based on activity of the magnetic field and charged particles interacting with it. So it's quite an active little world there. Let's go back to our Orion Nebula. So here's the core of that nebula again. But if you look very closely, you see not only a few bright stars here and there, but you see some fainter stars or stellar-like objects as well. Let me point those out. All right, so here's a couple you might not have noticed, but if you blow them up, you can see that, in fact, this whole region is kind of peppered with things like this. These are small stars trying to form, heating up. But we noticed, and this image is actually almost 2 decades old now, but we've noticed that stars that are still in these birthplaces all tend to have these dark, dusty regions around them, right? And it turns out that these dark, dusty regions are disks of dust orbiting the forming star. One is face on here. They can be a different orientation stuff. They're kind of flattened. So this one's face on to us. This one's kind of edge on. Their diameter is about the diameter of our solar system. All right. So it turns out that we now understand that these are the regions where planets form, and that stars and their planetary systems kind of form at the same time. And in fact, the study of these disks around young stars is a very hot topic in astronomy now. We have a couple of astronomers in the room who've done this. I won't embarrass them, but they're working on this right now. So here's another example, this time taken with that array of radio telescopes I mentioned to you in South America, where in the wavelengths of light that these telescopes can access, you can see into some of these disk regions around young stars. Here's one that was quite a surprise. This is an actual image from these telescopes, and the central stellar object is in the middle here, kind of buried in that lit up region. But you see that not only does it have a disk, but that the disk is arranged in rings, and there are gaps in the rings. And we know from our own solar system, like around Saturn, that has rings, that those gaps are sometimes caused or shepherded by moons. And so we wonder if there could be orbiting objects around stars like this that are causing these gaps in the rings, shaping the structure. So there's a lot of study right now as to how these disks would form and what the effect they would have on the formation of planets and vice versa. Old stars are active too, so they are exploding when they get old, or at least releasing their outer atmospheres. This one is releasing its outer atmosphere in a very beautiful, dynamic way. There's a kind of a constricting region of dust around the core of this star, and it's probably rotating as well. All of that contributes to the fact that as it releases its outer atmosphere during the stage of instability, that it's coming out in a kind of bipolar fashion. That is quite beautiful. So creative people have called this the butterfly nebula. All right. More massive stars, as they run out of their inner fuel, they become even more unstable, and as they begin to die, they will go through an explosive process called a supernova explosion. So this is basically the guts of a star being expelled out. The star itself exploded about 1,000 years ago in around 1054 AD, and so it's been quite a long time that we've even been able to monitor the debris coming out from this exploded star. There were astronomers in China and elsewhere at the original time that recorded seeing this brightened star in the sky. This is not only beautiful, but it is quite interesting because it's pictorially showing us what actually stars do. Stars shine because they have mostly hydrogen in their composition. They are very compressed because of the gravitational pull of this gas. Remember, they just formed out of these interstellar clouds, but they formed because gravity has pulled the gas together. So much so that the pressure inside is enormous, and hydrogen atoms can fuse to form helium. And there's a series of reactions, but the end product of that are photons of light that are released, and that's why a star shines. Eventually, though, much of that inner hydrogen has been used up in some of these reactions, and that kind of careful balance between inward pull and outward pressure, it becomes disturbed. And the star will go through a series of other reactions, and eventually, in the case of the largest stars, will explode. There's some outflowing phases before that as well. There are heavier elements even beyond helium in the periodic table that are produced in these processes. Things like carbon and iron, things we need for life, they get expelled. They're expelled into interstellar space. The next generations of stars that form out of this interstellar gas will again form mostly out of hydrogen, but they will have significant percentages, tiny but yet significant, of heavier elements that have been forged in previous generations of stars. It turns out that galaxies like our own have had several generations of massive stars come and go that have basically seeded our galaxy with heavier elements that can go into subsequent generations of stars. And that enables the stars and these dusty disks around them to form with heavier elements. Dusty disks are made of dust. They have solids as well as gases that include heavier elements in those gases. So stars are little factories for heavier elements that we need. They fill up galaxies, and galaxies themselves are active. So whole galaxies can be pulled together by mutual gravitational pull. These two are merging. It turns out that galaxy mergers were very common, especially in the early universe when spatial scales were tighter in and things had more of a chance to have gravitational influence one to another. So we can still see, as we look in distant space, evidence of galaxies merging. Most galaxies seem to be moving away from each other along with the expansion of space. But if there's a case where galaxies are close enough, their mutual gravitational pull will dominate that expansive tendency to move apart, and they will merge together. It can be a quite energetic process. Here's another pair of galaxies a little farther along in that merging process. And the interactions, the turbulence, the tidal forces have stirred up the gas, and that has basically incited a lot more star formation. You get a lot more eddies in this interstellar gas where stars begin to form. That's what all these bright lights are. These are the nebulae that astronomers, as I said, would look at and say, wow, star formation is still active here. So here's a pair of galaxies merging and becoming what we call a starburst, because so many stars are forming during this process. It turns out that as galaxies merge, there are not many or maybe even any star-to-star collisions, because the space between the stars is still enormous. But these forces will basically change the structure of these galaxies. They will eventually become one merged galaxy. They'll lose their individual spiral structures, usually becoming something more spherical. And if you think that this is all just interesting but, esoteric in a way, we now, last 2 or 3 years ago, astronomers realized that our nearest neighbor galaxy, the Andromeda galaxy, which is the nearest big spiral galaxy to our own, is actually on a head-on collision course to our Milky Way. So it appears that our Milky Way has had mergers in the past. We can tell that from the stellar populations within, and we will in the future. But like I say, modelers show that likely stars, individual stars and their planetary systems won't get destroyed. It's just the night sky will look very different in about 4 billion years when this will happen, all right? And we may have another problem to think about that before, which is our own sun may be burning out by that time. So we have some other things to think. Galaxies are active in other ways, in kind of interesting ways we would not have predicted. So this is a whole cluster of galaxies, these yellow things here. This is a whole cluster of distant galaxies. You can't see much detail because it is a distant cluster. Turns out clusters of galaxies are the most massive things that we know of, cohesive things in the universe. There's a lot of mass. Well, Einstein realized, smart fellow that he was, and his colleagues and peers at the time, that mass could actually distort space. In fact, even small amounts of mass distort space, but to such a small degree that we don't notice it. You and I are distorting space. But it doesn't have any really detectable effect for us unless we have a lot of mass together. So it turns out that this mass is distorting space, and most of the mass is not actually in the visible starlight coming from these galaxies, but is in invisible form we call dark matter. We don't know what dark matter is yet. It's still a very hot topic in astrophysics, but we can see its effects. So all this mass is distorting space. That means, see, I haven't yet mentioned this weird looking thing here. This weird looking thing is just a normal spiral galaxy in the background, but it's coming through the space that's distorted by this foreground cluster of galaxies, and this distorted space will act like a lens. It will stretch out and distort light from a background galaxy and even magnify it. So this more distant galaxy, we can see more detail about. If you don't mind its odd shape, you can look down here if you're an astronomer and actually see several apparitions of the core of this galaxy and study its composition, things like that in detail that we wouldn't have been able to see had it not been magnified by nature's magnifying glass. And also the amount of distortion of background light tells us something about where the dark matter is distributed in the foreground galaxy. So it's a way of studying dark matter, even though we don't know exactly what dark matter is. So this is called gravitational lensing, and it's a very, very active field of astrophysics right now, both to just study the gravity itself, but also to study dark matter and to study very distant galaxies that are magnified in this way. So speaking of galaxies, we are now understanding that the universe is actually enormous. Not that we didn't know that before, but in both space and time and the numbers of stars and galaxies. We think of each galaxy similar to our own as having a few 100 billion stars. And now we know that there are hundreds of billions of galaxies in our observable universe. So if you do the math, that's a scientific notation with a lot of zeros represented there. There's a lot of stars in the universe. What does that look like? So this is a very famous image from the Hubble telescope. It's called the ultra deep field. Deep fields are made basically by simply observing for a long time. So you can receive fainter and fainter light from the distant universe. And that allows you to see very faint distant galaxies. So this is a view that's about the width of a drinking straw in the sky, but taken over several days of receiving light with this very sensitive telescope. The result is this image. These are not stars for the most part. There's a couple of stars that are in the near field of our own galaxy here and here. But for the most part, every little blip of light here is a galaxy, an entire galaxy external to our own Milky Way. And it's just mind-boggling. If you imagine this extrapolated all over the entire sky, we have a universe that is literally filled with galaxies. Here's a spiral here. You see different shapes. If our own Milky Way were in here, it would probably look like one of these spirals, but of course we can't get far enough out of our Milky Way. We can't get out of it at all yet to take a picture of it. It is fantastic to behold. And then to realize that these galaxies are not all at the same distance from us. Some are farther away than others is another aspect of this, because we're seeing each of these galaxies not as they are right now, but as they were when the light began its trip to us. So this is a look back in history, and we're seeing different epochs of history all at the same time, depending on the various distances of these galaxies. In fact, trying to discern the distances of galaxies is difficult, but it's a very important job that astronomers are doing. People have been inspired by images like this. Front cover of USA Today, with all its bad news, also had this deep field a few years ago. Even the Huffington Post had a moment of reverence and said, "Holy Hubble here." So what's happening is our telescopes get better. So this is what this graphic is trying to show. As our telescopes get better, we're able to see farther distances, which means seeing farther back in time. All right? So this is just representing back in the 1990s and before with observatories, we could see to a certain degree of sensitivity, so to a certain faintness, which meant certain distances of faint galaxies. With space telescopes and improved cameras on the space telescope, over the years we were able to see fainter and fainter galaxies because the detectors were more sensitive. So then we could see more distant galaxies because they were fainter in appearance because they're more distant. That's what these arrows proclaim here. Well, that's equivalent to looking back in time. So the scale on the bottom here is time going from right to left. So if the universe began somewhere off to the right here, we're starting to see baby galaxies come together toward the very beginning of the universe, close to the Big Bang. The beginning of the universe, we think, happened, at least as we understand the universe, back when physics didn't work the way physics works now, but was about 13.8 billion years ago. There's several different lines of observational evidence for believing that that's more or less the age of the universe. It's still being studied very heavily. We are now able to see baby galaxies forming out of the earliest gases that formed as the universe cooled from within the first 0.8 of that 13.8 billion year history. So this is quite incredible. That's what this graphic is trying to show here, is that after the first energetic burst of time and space, as we understand time and space, the universe expanded rapidly, it cooled, gases were able to form, and early on stars were able to form, and then gravitational eddies of this gas and dark matter and early stars formed to become what we call proto-galaxies, and then those galaxies would merge and grow over time. And we're able to see some of those baby galaxies forming early on. And the James Webb Space Telescope being launched next year will be an infrared telescope that should be able to see even earlier, even more into this era of baby galaxies forming. We can compare what these galaxies looked like in the early universe with what they look like closer to our own time and in our own galaxy, and see if they've changed, and in fact they have changed. So as I told you, stars are like little factories that create heavier elements. Generations of stars actually enrich their galaxies with heavier elements over time. So if you look at a very distant galaxy and use a spectrograph to stretch out its light into its constituent colors, you'll see the patterns mostly of hydrogen, and you'll see that there's a little helium, a few other elements, but nothing major. If you do that same analysis of galaxies closer to us in time and space, these galaxies have had billions of years for stars to come and go and enrich their content. Those galaxies in our own have stars that, yes, are mostly hydrogen still, but we can see a lot more evidence of other things like carbon, iron, oxygen. They've also grown. The mergers over time have made galaxies, individual galaxies, bigger. By merging with others, they've had time to take on interesting shapes and sometimes spiral shapes, such as we're familiar with. So pulling some of these galaxies out of the deep field and then distributing them visually so that you can see the difference, I think this image is very helpful. So these are galaxies whose distances have been gauged by various techniques that astronomers use. And you can see that the ones closest to us in space and time are bigger, and then as you go out 1 billion light years, 4 billion light years, 6 billion light years, 8 billion light years, 10 billion light years, you see that the galaxies are different. They are smaller. They haven't had time yet in the early universe to take on the bigger shapes. And of course, as I mentioned, their compositions have changed and been enriched over time as well. The universe has changed over time, and we can actually observe that with telescopes. It appears, therefore, that the universe has developed over time and continues to mature and change with the production of stars and therefore heavier elements, and that enables the formation of planets and stars in our epoch of time, because stars in our epoch of time form with these heavier elements. That enables these dusty disks to form around stars and planets to form out of those disks. And this provides conditions needed for life to thrive on at least one planet. And this enables unintelligence like this to happen on this planet. There we go. All right. So how are we to take this? The universe has matured over time. I use that word mature, but it's changed over time. Now we have conditions for life to thrive. Does that mean there was a purpose and is a purpose to the universe? I have just jumped from the science. Everything I've said up to this point has been basically our current astronomical understanding of the universe. I have jumped to a philosophical question, all right? Now, I hope that's kind of obvious, but it isn't obvious to a lot of people. A lot of times these questions get intermingled, and they seed one another. Here was an interesting project done by the John Templeton Foundation where they asked several thought leaders of around the world if they thought the universe has a purpose. And they got an entire array of answers from all of these brilliant people. So I won't, what's more interesting than these one-word answers is that each one of these wrote an essay about why they answered it the way that they did. But there are scientists here, philosophers here, and theologians here in the group. And some said no, that's even a silly question. I mean, that this idea of purpose is really no longer a respectable question in our world where we believe we can actually analyze the physical causes and effects of everything, and to ascribe purpose to it is really meaningless and not helpful. Others would say, here's Owen Gingrich, who's a professor of astronomy and the history of science at Harvard. He says, yes, he cannot imagine why anyone could look at the universe as it has evolved as it has and not be filled with the sense that there must be a purpose for it all. I mean, we're having this conversation, for heaven's sake. There must be some reason why the universe has produced self-reflecting life. Others are not quite sure. They don't know exactly what that means. Neil deGrasse Tyson said, well, I'm not sure. I think, it depends on who you ask. If you ask your gut bacteria if there's a purpose for humans in the universe, they would say, yes, the purpose of the universe is to create humans so that they will have bowels in which we, the gut bacteria, can thrive. So what is purpose? Others had very more nuanced answers. So I just point this out to say that a philosophical question can elicit different answers even from scholars who might all agree on the science, right? So that's something to keep in mind. Here's what Freeman Dyson, the physicist, said. It would not be surprising if it should turn out that the origin and destiny of the energy in the universe cannot be completely understood in isolation from the phenomena of life and consciousness. What is consciousness? Why do we have creatures like ourselves formed out of the material that was forged in stars, and yet here we are thinking about it? What does that mean? He said, and the design of the inanimate universe may not be as detached from the potentialities of life and intelligence as scientists of his 20th century have tended to suppose. All right? So how does this all fit together? I don't know. So we're going to move on to some more science, all right? The universe always holds some new discoveries and mysteries, surprises and questions. The more we're discovering, the more questions it gives us, and that's a wonderful thing. Just last year, we celebrated the discovery of gravitational waves. So this is not really a surprise in the sense that ever since Einstein's theories of gravitation were forged, there was an idea that information might be able to be conveyed through means not just electromagnetic radiation, not just light from the electromagnetic spectrum, but also in other ways, that gravity itself and disturbances of mass could create waves of information that would create waves of disturbances in space-time itself. And so this actual disturbance of the merger of two black holes, graphically depicted here, was actually measured. That's what these signals over here are portraying, are the signals measured by instruments on the ground that were designed to measure distances between two laser producing or receiving instruments. And they could measure the distances that the laser light traveled back and forth very precisely. But if distances change ever so slightly, the timing would change ever so slightly. And these instruments, after years and years and years of watching and waiting, finally detected exactly the signal that had been predicted by theoreticians that they should see if somewhere off in outer space there was a great disturbance of a merger of two massive things like two black holes, which are the cores of very massive collapsed stars. They have a very strong gravitational field. So this was an exciting discovery, and so now we're trying to hone in on being able to isolate the sources where these waves originate from other types of mergers, and learn more about them. I mentioned they're trying to figure out what dark matter is. We know that it's there, but we don't know what it is. We also want to understand dark energy. That's something quite different. Dark energy is actually this strange force or energy that seems to be compelling the universe to expand at greater and greater rates. So the universe is accelerating. Here's our deep field again. When I was in graduate school, the understanding was that galaxies were moving apart from one another because they were embedded in space that is itself expanding, but that expansion must be slowing down because all this matter would be pulling on each other, on itself, and that expansion therefore would either slow down forever or else it would actually reverse in on itself. The surprise was the detection a few years ago by looking very carefully at the apparent outward velocities of distant galaxies and nearby galaxies as they're carried along with the expansion of space, that for the last few billion years, the expansion of the universe has been getting faster. So here's a model. Here's the kind of picture of the idea of the universe eventually initially expanding and then crunching back in on itself, or expanding but slowing down at that expansion forever. These were the two choices we had when I was in grad school. The third choice that seems to more accurately represent the data is that the universe did initially decelerate after the Big Bang, but now has become more dominated by a tendency to accelerate in that expanding motion. We don't know what this is. It may be an aspect of gravity that's repulsive. So right now we just call it dark energy, and these three gentlemen here won a Nobel Prize for discovering this, but now we have to figure out what it is. Much closer to home, we're finding evidence of interesting possibilities of places to look for life. This is a moon of Jupiter called Europa, a picture taken with a probe called Galileo. But just recently, the Hubble telescope has seen evidence, very faint, but of plumes of water vapor being expelled. This is an icy moon, so it would be expelled between cracks in the ice. Now, many have thought that there might be an ocean under the ice of Europa. And of course, if there's water, then there might be life, but how do you get in there to study that water? Well, it would be quite convenient if the water vapor were actually being expelled. So these plumes are being actively studied right now to see, they seem to be periodic, or at least they're not constant. So, could we send a probe to sample the water that way? And of course, we're interested in looking for life beyond our solar system as well. This age-old question, are there other planets in the universe? Is there another Earth out there? Could there be life? We don't know yet if there's life beyond planet Earth, but we're certainly interested. People have been interested in this for a long time. So Greek philosophers speculated about it. Epicurus thought there are infinite worlds, both like and unlike this world of ours, and we have to believe that in all these worlds there are living creatures and planets and other things. So when he's talking about world, he's obviously not using it the way we do, but nevertheless there was imagination. And fast forward a few centuries, Bruno felt that there might be countless worlds in the universe, no worse and no less inhabited than our Earth. So people were thinking about this a long time. He got himself into some trouble, but he was thinking about it. All right. There he is, Bruno. People still bring roses to him in Rome there. I discovered people have been asking this question from antiquity. So here's a couple of anthologies of work, speculations about life beyond Earth going on for millennia, actually. All right, I'm trying to try to finish here in about 2 minutes, yes. 2 minutes for the rest of the universe. Let me just say that this is a very hot topic right now. The study of planets outside our solar system. Why? Because when I was in graduate school, we didn't know of any planets outside our solar system. And now, because the technology has improved, we know of thousands. And not only that, but we can actually do statistical studies of planets, planetary systems around other stars. And so we can say now that on average, every star in the galaxy probably has a planet. Some don't have any, and some have more than one, like our own sun. But planets are very common. And if there are, something like 200 to 400 billion stars in our galaxy, and every one of them has a planet, that's an awful lot of planets, all right? That's the discovery rate growing and growing every year. Let me just kind of fast forward to this. We're finding more Earth-like, maybe, planets. This system announced recently called TRAPPIST-1, which is the name of the survey that's been looking, one of the surveys looking for planets. It found a whole array of planets around this one star, and these planets are more or less Earth-sized. This is an artist's impression. We don't really know what they look like, all right? But 2 or 3 of them are just the right distance from their parent star to be in the habitable zone, meaning they could have liquid water. Doesn't mean they have life, but they might. So we're very curious. All right, and then as this field progresses, we're looking at the atmospheres of these planets, exoplanets as we call them, to find out if they have evidence for biological activity. As our telescopes get better, we'll be looking for evidence of oxygen, liquid water, reflected light that looks like what we see when we look back at planet Earth from plants, methane that's produced by biological activities. Looking at all this as kind of evidence that works together to suggest that there might be biological activity on one of these exoplanets, and of course rule out other explanations for these types of things. Let me just point out that religious groups around the world are quite interested in this. The Catholic Church held a whole scientific conference on astrobiology a few years ago, bringing scientists and theologians together. The cartoon was in the Washington Post, I guess making a little light of this, but actually it was a quite serious scientific conference because Father Funes, who directed the Vatican Observatory, was asked, why is the Vatican involved in this new field of astrobiology? And he said, although astrobiology is an emerging field and still a developing subject, the questions of life's origins and whether life exists elsewhere in the universe are very interesting and deserve serious consideration. These questions offer many philosophical and theological implications. And of course, for Christians, one of the questions is not only could God have made a fruitful universe with life everywhere, as I believe is certainly possible, but what is the role of Jesus Christ? In Christian theology, Jesus Christ is central to the faith. Christ is responsible for upholding the universe and also for redeeming it. And so would this be a case that the same Christ that manifested himself in human form on planet Earth would be manifest throughout the universe, and in what way? These are interesting theological questions. Even the Library of Congress in the U.S. has considered this. All right, I'm going to just fast forward, say that C.S. Lewis thought about whether or not finding life elsewhere would be would change people's worldviews in great ways, and he seemed to think that people would end up where they started, one way or the other. All right, I will close by saying that the universe does inspire. The heavens declare the glory of God, says the psalmist in Psalm 19. The skies proclaim the work of his hands, and they do it without speech. They do it without words, and yet their voice goes out into all the earth. I certainly believe that is still the case. And people are celebrating how they are inspired by the universe. I gave a talk like this in Canada. One of the people in the audience was a woman from Iran, an artist, and so she reflected on these thoughts that evening and created this piece of art of dancing. She felt the galaxies to her looked like beings dancing in space. People have been inspired for a long time, so this is something I just learned about last week from an astronomer right here in Cambridge. Marco, are you here? Yes. There's Marco, yes. So Marco studies these disks around young stars here at the Institute of Astronomy, but I believe this is your hometown, Ravenna, is that right? So in Ravenna, there's this famous mausoleum. I think it's 1,500 years old at least. But inside, the beautiful artwork inside, and on the ceiling, there's an image of stars that most people who understand astronomy know that if you point a telescope at the North Star and just let it collect light, you'll get these circular patterns of the light around in a circle around the North Star. Well, on the ceiling here, there are these circular patterns of stars, but right in the middle is a cross. And the idea here, as Marco's friend told him, sorry Marco, I just took it straight from your email, is that when the artist created this, however long, many centuries ago, the idea was that the cross would be in the center of this navigational wonder, the North Star that everyone was using for navigation. The circles represent the motion of stars. The symbolic meaning is that the polar star is Christ, the centrality of Christ and the centrality of this whole navigation. And so you can actually translate that. People have been inspired to think of this as how they might navigate their lives as well. I will just mention my friend Gladys, another astronomer who takes astronomy lessons to an orphanage in Asia every year, and these kids are very excited to hear about space, so science can uplift. I think I'll end it there, but I do want to just say that we live in an incredible, inspiring, and fruitful universe. Thank you very much.